Good morning to all. It is pleasure to introduce today's chief guest, Professor Dr. A. Meenakshi, Department of Mathematics, Veltek Rangarajan R&D, R&D Institute of Science and Technology, Chennai. Our research person having 22 years of teaching experience. Her academic responsibilities are MBA and NAC coordinators, symposium organizer, research supervisor, syllabus reviewer, and DC member. Her research areas are domination and labeling in graph theory, fuzzy graph theory, modeling in hybrid graph. As a research person, she has given guest lecture in reputed institutions. She has published 2 books, presented 56 research papers in national and international conferences, and published 32 research papers in Scopus and Annexer 1 journals. She is also reviewer of Advanced in Mathematics and Computer Science, Intelligent Journal of Physics and Systems, Asian Journal of Mathematics. I welcome you, ma'am. Now the session is handed over to Dr. A. Meenakshi.
Thank you, ma'am. Thank you for your nice introduction. I share the screen. இந்த பார்க்குறேன்.
The, con- the container is explanation. I have everything. Everything, everything. Bharatiya University.
Am I audible, sir, Kannan sir?
Audible, ma'am, audible.
Yes, yes. Good morning to all. Sorry for the disturbance happen here. So I'm happy to share my knowledge. Today's my title is Applications of Graph Theory in Networks. So what is a graph? So I'm considering the organization. In that organization, senior manager named as B. Under the senior manager, team leader and team leaders are assigned under senior manager, team leader 1, team leader 2, etc. Team leader N. So under team leader 1, N1 trainees are there. Under team leader 2, N2 trainees are there. Under team leader N, NN trainees are there. These are the relations I quoted here. That's the meaning that there is a relation between senior manager to team leaders, and each team leaders have some trainees. So this is the organization model I am representing. This is the graph. So graph is the graph consists of non-empty set of vertices and edges. Here the senior manager, team leaders and trainees are the represented as the nodes, and the relation between them represented as the edges. So this is the connected graph. Why? Because if there is a path between every pair of distinct vertices, then it is connected. Here there is exactly one path between different pair of vertices. So it is connected, and it is also a tree. By the definition of tree has n vertices and n minus 1 edges. So according to that, and also we can say that there is a unique path between every pair of distinct vertices. And also I'm applying here n vertices and n minus edges. N vertices are B, TL1, TL2, etc. TLN. That is B, comma N vertices. Team leaders N vertices are there, N vertices. And under each team leaders, the trainees are N1 trainees. From team leader to N2 trainees. From nth team leader, we have NN trainees are there. So the number of edges present here is N plus N1 plus N2 plus etc. plus NN, and whose sum is 1 less than that of the vertices. So it is a tree. So I'm making the visualization of the organization model here. So the graph, which consists of the non-empty set of vertices and edges. I hope for that. And what is the necessity to represent that each object as a model is? So we know that the world, when we cannot see the world at a glance, is it? So we can represent the world as a symbolic representation. We make it in a single paper, that is a graph. In that graph, nodes are there. So in the world, I'm talking about, you can take the states or cities, that is the way joining from one state to another state, we may treat as a link. So we can represent what is in our imagination. That imagination we can bring it out as the graph. So that one only I am representing here. Now we'll see what are the applications of graph theory. So we are, whether the PPT is moving. Hello, am I audible? PPT,
No, ma'am.
PPT is moving or not?
No, ma'am.
No, ma'am, no. Applications of graph theory. I am in applications of graph theory. Whether the PPT is, yes, sir, yes, sir, yes, sir. Oh, say thank you, sir. So we are looking at the applications of graph theory. So I am representing. We are representing the that is the graph is a model of network, chemical structure, and then social network and biological network. So what does mean by network? So network, which consists of the non-empty set of nodes and links. So when we give the when will the link will be present here is there is a knowledge sharing between every pair of vertices. The corresponding link will be present in the network, otherwise not. So probably for the network, so each and every vertex should share the data or share the knowledge or share the information to others. It will be benefitable one, otherwise not. So this for the example of network, I'm going to that is a main part of talk today. That is a application of the network. So we'll see at last. I am explaining detailed with an example which is related to my research work. And now I'm moving to chemical structure. So chemical structure of chemical compounds can be represented as a graph. So what is the necessity to represent this chemical structure in terms of graph is to find the topological indices. So what does it mean by topological indices is this is one of the connectivity index which is based on the which is calculated based on the chemical structure of the chemical compounds. And also the topological indices analyze the properties of physical properties of the chemical compounds such as melting point, boiling point. I hope some of the disturbance is coming. So topological indices is is used to analyze the physical properties of the chemical compounds, such as boiling point, melting point, electric conductivity, and then hardness of the compounds, and then density of the compounds. So used to this one, we can analyze what is the type of what is the we can analyze the physical properties, and also the topological indices is used to develop develop QSAR, that is quantitative structure analytic. Sorry, QSAR, that is quantitative structure. What, sir? Am I audible? Yes, sir. QSAR, it is quantitative structure activity relationship, which is a computational modeling method which gives the relation between the structural properties of the chemical compounds and biological activities. So I'm here we are representing some of the chemical structure of the alkynes. The first one is the methane. Its formula is CH4. So that what I marked the right hand side, that is the model of the methane. That is what I marked as red,
Excuse
that
me,
is a
ma'am.
carbon.
Sorry to
Yes,
disturb you.
yes, sir.
Ma'am, your voice is audible, but PPT is not moving.
So echo coming in.
No, ma'am.
Hello.
Voice is audible. Voice is very clear, but PPT is not moving, madam. Am I audible to you?
PPT is not visible. Huh?
No, it is visible, but it is not moving. It is still in slide 3. It is still in slide 3.
Oh, I'm sorry.
I think you are talking
It's a
from slide
chemical
4,
compounds.
representing the picture from slide 4.
Yeah, sir.
But it
So
is
it's
in slide 3
still in.
for the presentation. Yes, it is not moving.
I'm in slide 3 only, sir. I'm just
Okay.
yeah. I'm not pasting everything on the PPT. Just I'm explaining. So is it okay?
Okay.
Okay, sir.
Ma'am, yes, ma'am. It's
Yes,
better you start the slideshow, ma'am. You
yes, sir.
place
Please.
the
Yes,
screen in
yes,
a
sir.
slide
Yes,
in
sir.
the
Yes,
slideshow.
yes, sir. Yes, sir. Yes, sir. Now it's okay. Please, can you tell me, any one of you?
Yes, ma'am. Yes, ma'am. You can
Is it
continue.
okay? Yes, I'm sorry. I'm sorry for that. So that we discussed, I started that chemical structure. So this is methane. So methane, that chemical formula is CH4. So one of the carbon is that is surrounded by the 4 hydrogen molecules. Yes. And the next one is methane. So this is a graph model. This is a graph model. Next one is ethane, C2H6. Its chemical structural formula is CH3. So it is this graph is based on the chemical structure of the compounds. Okay. So CH3. So the red color carbon is surrounded by 3 hydrogen molecules, black color, which has been marked as black color. And next another one CH3. So we marked here. Next one C3H8, which is propane, which is also same way, whose chemical structural formula CH3, CH2, CH3. And the next one is butane. For butane formula is C4H10. And the chemical structural formula is CH3, CH2, CH2, CH3. So which is represented like this. This is a molecular graph of the alkyne butane. Molecular graph of the alkyne butane. So CH3. So how we represent in terms of graph is according to the chemical structure. CH3. So C, this is H3. Next to CH2. So middle C, which is surrounded by 2 hydrogens. And then CH2, again this one. And then CH3, C, which is surrounded by. So next one, social network analysis. So how the graph can be represented, how it can be, what are the applications in social network. So social network, which gives a relation uh, between the social entities. The entities may be person or group or website or United States or scholarly publications. So the social networks are also used in the spread of the diffusion of innovations, news and rumors also. So diffusion of innovations is for that is a that is we have to that familiarize or popularize the innovations very speedily throughout the population. So within a fraction of second, so it will be reached to all. So maximum number of population it will be reached. And this social network also used to that is nowadays and this social network plays important role in that is spreading the that is behavior activities of diseases also. Okay. So during the corona period, that is March, after March 22nd 2019, we were in home due to corona lockdown. So we don't know about what is corona. We heard what is that which is which is arises from that is China, like that we know, but we don't know about the clear picture of corona. So what are the precautions we have to do? We need immunity for that. So what are the types of food we have to take? So when we go out, what are the precautions we need? So what are the medicines are there? What are the Siddha medicines are there? Which hospital is better? So we have so many questions which has been arised in our mind. So we don't know about that because much earlier, if we faced this same type of problem, then we know about that. We have some experience we got from that, but we don't know about that. So what we have to do through the social media, from the that is television, from the that is newspaper, and from the WhatsApp group mainly. So using, so from the WhatsApp group, what we received, that information we have to accept it, whether it may be rumor or not, that we have to accept, we abide, and then we protect ourselves. Okay. So this is the that is application of that social networks, which is represented in terms of the WhatsApp group. Suppose WhatsApp group is there, how we reached this FDP up to the 1,000 members is, so they make they created the link and then they posted in some other group, and then everybody joined. So the organizer is the node, and then from the node we are getting the information. Those who join, that also nodes. So what are the messages, what are the information passed, that is acted as a link here. So this is a social network. Next one, biological network. So in that biological network, it is also one of the type of the social network. And here especially we are that is like that is network motifs. activity motifs. What is motifs? Motifs are the small subgraph which formed some local patterns over 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 presented in the biological network. Okay, so there is activity motif also. It is a there is activity what happened between the nodes and the nodes and edges. Okay, here the nodes acting, the nodes are here we are considering the nodes are the organisms. So we here it also analyzes the local pattern such as food web. So I said food web is an example of the network motif. So food web, we know it is interconnected between some of the living species, and which creates some pattern. From the pattern we follows this pattern, which allows us to visualize the nature of the species, what has happened, what is that is existing in the world. So this is a biological network. So here we mentioned some of the that is graph terms. So for metabolic signaling pathways, a path is used, and that the protein complex clicks used. Clicks is a small is the that is like a complete graph. Okay, and hubs. So for regulatory models, hubs used. Now I come to back. This is a application of the network. So this is a what we are doing here is we are created the network. In that network we hide the secret number or password. Who want to break the password, they should know the concept based on the domination. So this is a this is the that is a what is this is a point I have to convey here. So how to construct the network? So what is the necessity to construct this network is, so nowadays we are everything is based on the password. When we open that mobile password, when I open the that is a network banking password, so whatever it's so the password is important today's world. So the password, I'm treating my password as a secret number. It's a numerical value. So the numerical value, I have to spread over this numerical value in the network. And who want to know break it, they should know what is mean by domination. Here I'm applying efficient domination. This is the aim of this today's speech. So this we are taking that G is a simple graph of a finite order, and a set of all vertices is denoted by V of G, and set of all edges is denoted by E of G, and the degree of the vertex is denoted by D of V, and N of V represent the open neighborhood of the vertices. N of there is a next one is closed neighborhood of the vertices V, and that induced subgraph of G, let S be the subset of the vertex set V, and for the set S corresponding, the induced subgraph is denoted by the induced symbol of S, and the minimum degree maximum degree is represented by small del of G and capital del of G, and the domination number of G is represented by gamma of G. Gamma of G represent the minimum domination number. So what does mean by domination? What does mean by domination number? So let G be a graph which consists of the vertices whose set is V of G. A subset S of V of G is said to be dominating if every vertex in V of S is adjacent to at least one vertex in S. So the minimum cardinality of the S is said to be domination number and is denoted by gamma of G. Let us consider the graph G. Here I'm considering this is the graph I'm taking, which is G. So for this, the possibility of the dominating sets are, I can say 2, 4, 7, 8, 6. Next option is 1, 3, 5. That only represented here. Another option 1, 3, 6. Another one, I can say 1, 1, 3, and then 8, and then 6. Okay, so we can list out more. But among this, which set gives the minimum cardinality, that we can take it as a dominating set. So for this one, 1, 3, 5 is the dominating set. You can say take 1, 3, 6 also. So the domination number of this G is 3. Next, what is efficient dominating set? This is the important thing here. This efficient dominating set is a plays a very much important role in network. So we can see here. So what is the efficient dominating set? So a dominating set S is said to be efficient if the closed neighborhood of every members present in S whose intersection is equal to empty. Okay. So in this efficient domination, the dominating set is unique for a graph. Okay. Now, for example, I'm consider the graph G, and the vertex sets cardinality of G is 11 vertices, and the edges, which is you can see in the graph. So efficient domination is only V3, V6, V11. For the previous graph, we discussed so many possibilities for dominating set, and for even minimal also we discussed two cases. But here, this dominating set is unique since V3, consider V3, and whose closed neighborhoods are V3, V1, V7, V4. And for V6 is V6, V2, V10, V5, and for V11 is V11, V8, V9. So if we take the intersection n of closed neighborhood of n of V3 intersection closed neighborhood of V6 intersection closed neighborhood of V11 equal to empty. So that's why it plays so very much effective. It plays effective role in the network. Now, as I said, so secret number. So we have to find the one of the secret number. That is our wish. We may take it. N is a secret number, which is not equal to 0. We should be positive. Okay, n of the secret number. We can take any number, but for the first case, I'm taking n is concurrent to 0 mod 3. We can change the mod also. Mod 5. We can try for mod 6, mod 7. So very fundamental work. This work I done during 2015. This is a now split the secret number n. I am taking concurrent to 0. Second case n is not concurrent to 0. N is concurrent to 0 mod 3 into 3 partitions. Why 3 partitions is here I am considering under modulo 3. This n is under modulo 3. So that's why 3 partitions are there, and assign each part in the edges which is incident to the efficient dominating vertex set of order 3. Here order 3, here mod 3. So therefore 3 partitions are there. Therefore I'm setting for my network whose efficient domination number is 3. Okay. So show that n is equal to summation I is equal to 1 to kn f of u xi plus summation j is equal to 1 to k2 f of v yj plus summation k is equal to 1 to k3 f of w zk, where uxi, vyj, and wzk belongs to k. That's the meaning that for u, the neighbors are xi. For u, for the vertex u, the neighbors are xi. Okay. And for v, the neighbors are yj. And for the vertex w, the neighbors are zk. So I'm defining here f of u xi. For that, f of u xi means which represent the edge. Okay, f is a map from e to the n, e to n. Okay, I will represent in the next slide. So now I'm constructing the graph whose efficient domination number is 3. Okay, because I'm taking n is concurrent to 0 mod 3. I'm going to consider the network. In this network, efficient domination number is 3. So J is a simple graph with the cardinality V of G is equal to P, and its edge set cardinality is Q. S is equal to UVW, efficient dominating set of G with the fixed degrees. This fixed degrees depend on U. I fixed here degree of U is K1, degree of V is K2, degree of W is K3, which is fixed first itself. Then only we can construct the network. Where K1, K2, K3, etc. K1, K2, K3 greater than or equal to 1. So UV, first we are starting the network with the vertex U, V, W. Okay, U, V, W. and the corresponding neighbors. I have to assign the corresponding neighbors, and then what are the edges I need, how many number of edges I need, we have to decide ourselves. Okay, now for the vertex u, x1, x2, etc., xk1, y1, y2, etc., yk2, z1, z2, etc., zk3 are the neighbors of u, v, w respectively. So I can say another way than distance between u and xi, and distance between v and yj, and distance between w and zk equal to 1, where I lie between 1 to k1, j lie between 1 to k2, k lie between 1 to k3. Always this is the thing. I lie between 1 to k1, j 1 to k2, k 1 to k3. Now this is a preview of that network. Just I didn't complete, just for your understanding, just I inserted this network. Look at here, this is u. How we frame this, n is concurrent to 0 mod 3. So that's why three efficient dominating members present in my network. That is, let it be UVW. Okay, so for u, as earlier in the previous slide we see, that is neighbors of u are x1, x2, etc., xk1. Here k1, one is also not clear. So k1. So for u, k1 neighbors are there. For v, k2 neighbors are there. For w, k3 neighbors are there. Okay, now define vertex set. So vertex set is defined here itself. So what are the vertex of this network? U, V, W, and its neighbors of U is K1, and neighbors of V is K2, and neighbors of W is K3. That only we written here. V of G is equal to UVW. These are the members of the efficient domination. This three will be present in the efficient dominating set. Is UVW, and that union, that xi, the neighbors of u running from I is equal to 1 to k1, and the neighbors of v, yj, j is equal to 1 to k2, and the neighbors of w is zk, so k is equal to 1 to 2. So cardinality of v of g is equal to these three members u, v, w, these three members plus k1 plus k2 plus k3. Now the vertex we define for the network. Now the edge set. So we know that the number of possible number of maximum number of edges present in the complete graph. Here also we can follow, but it should be subject to some certain conditions. Why is, if uh, I that is plan for all the edges, it violate the efficient dominating set. Why? Because that is neighborhood of u intersection neighborhood of v intersection neighborhood of w should be is equal to mt, then only uvw will be the member of the efficient dominating set. Otherwise we cannot, so it will be breaking. So that's why what I'm discussing here, minimum number of edges will be present, what is the maximum number of edges will be present in the network, that I denoted here. Now first I define e1. So what is e1 is, E1 is xi yj, comma yj zk. So for this network, what are the edges needed? Okay, that is it is not going to be disconnected. So for that, what I need? So xi yj zk, or another option is there, xi zk, xi. I'm sorry, here xi zk and yj zk. Okay, here the wrong here. I written the same one for only one ijk, where as usual I lie between j lie between k lie between k1 1 to k1, 1 to k2, 1 to k3 respectively. Okay, so what I marked, this is this one. So xi yj, here look at xi yj. Here I marked only one. That's why I said xi yj. Any one if you join, no need to join all the one. Okay, which will be there is connected one. For that purpose I'm thinking this xi to yj. So anyone yj to zk. Okay, that only written here. And then minimum, what is a minimum number of edges? So I have to say, if I keep the network like this, that is a no, that is a how can I call? There is a no curiosity will come to find out what is that in that network. So if we place more number of edges and under the values which will be getting some confusion state, then only the network will be a very good network. So for that reason, that is e minimum, that is e minimum is equal to, I am setting another set edge set, e minimum is equal to uxi vyj wzk. Okay, so in this previous one just I am mentioning xi yj zk only. Okay, here uxi, so u is the middle one and its neighbors are xi, so uxi vyj. Okay, like for the second one, second vertex, the second member of the efficient dominating set, v and its neighbors. Okay, and w is zk, they are talking about this one, what I marked in red color union, what I marked in blue color, and what I marked in green color. So that edges, this edges union E1, which is the minimum number of edges. That only I marked here. That only I marked here. Okay, this whole thing represent the this whole for the whole network. This number of edges enough. Okay. So now for that E minimum, that what is the cardinality of E minimum is this is K1, K1, because for you neighbors of you are xi lie between 1 to K1, so K1 I marked. K1 for this one, K2 for this one, K3, and then for E1 for that E1 here under modulo 3, so we need only two edges, that two edges enough for that. So I'm putting here cardinality of E minimum is equal to, I'm saying alpha, where alpha is K1 plus K2 plus K3 plus 2. And then E max, now I'm defining E max. So what are the edges? We know how to draw the complete graph. So I have to join every vertex to every other distinct vertices, okay, without violating the efficient dominating member. Okay, so what I did is I'm drawing the complete graph for the number of vertices what we denoted, that is K1 plus K2 plus K3. Okay, that is K1 plus K2 plus K3 plus 3. For that, we are drawing that maximum number of edges. That is, I am framing the complete graph. From that, what are the edges is going to be subtract, we will see. Okay, so look at here. I cannot join U to V directly. I cannot join U to W directly because it violates the efficient dominating set. Okay, if I join, it cannot be act as a member of the efficient dominating set. So I cannot join U to V, V to W, W to U, and also U to V neighbors, U to V's neighbors. That is, I cannot join U to YJs, where J lies between 1 to K2. Okay, I cannot join U to WK, where K lies between 1 to K3. Okay, likewise, I cannot join V to XI, V, the vertex V to WK. Likewise, W to XIs, W to YJs. So these are the restrictions are there. Now you can see, you can easily understand. So that's why I subtracted UV, VW, WU, UYJ, UZK, VXI, VZK, WXI, WYJ, where IJK lies between 1 to K1, 1 to K2, 1 to K3 respectively. Now this Emax we calculated. So according to that, the number of edges present in the complete graph is NC2, and then minus, I'm subtracting this one, I'm getting the value beta, where beta is 1 by 2 into K1 plus K2 plus K3 into K1 plus K2 plus K3 plus 1. So edge set E of G, cardinality of edge set is lies between alpha to beta. Now again I drawn this one. So for the next, now we are looking encryption algorithm. Using encryption and decryption, we have to break and then break that secret number. What we are going to represent here. Okay, that encrypted number n is concurrent to 0 mod 3. my input is n is greater than or equal to 3. So our secret number will be greater than that of 3. N is concurrent to 0 mod 3. Output is, if I'm giving input, output I'm getting the encrypted labeled graph. Okay, labeling also here we are going to apply. So encrypted labeled graph G. Now first step, the secret number n is splitted into 3 partitions. How we splitted? So here I'm giving n naught is concurrent to 0 mod 3. Okay, so n naught here I'm taking the case n is concurrent to 0 mod 3. So here I'm selecting the suitable secret number. We cannot just like we cannot take all. Okay, so n is concurrent to 0 mod 3. So this is split the number n into 3 partitions. Say n naught concurrent to 0 mod 3. First I separated this n to 3 partitions. So first partition named as n naught, which is concurrent to 0 mod 3. N1 which is concurrent to 1 mod 3, N2 which is concurrent to 2 mod 3. So according to that, I split it. Now what I have to do? I'll, keeping with the N0, N2, etc. Now the construction of G already we discussed. Now how to labeling the graph using this N0, N1, N2. Okay. So split N0 to K1 values, split N0 to K1 values. This K1 values will be placed on the UXIs. Okay, UXI, because U's neighbors are K1 members are there. That's why I represented here K1. N1 is equal to, and next one. Okay, N1 is concurrent to 1 mod 3, which is splitted sub partitions into K2 numbers. So like B1 plus B2 etc. up to BK2. And N2 is concurrent to 2 mod 3, which is splitted to K3 subpartitions, K3 elements I'm splitting. Okay, next step. So F is a map from vertex, edge set to the edge set to N, which is a bijective map clearly. E is the edge set and N is the non-negative positive integers. This N represent what we are going to partition, sub-partition that values. Okay. Now I'm defining. So for what, which edge I'm going to assign which value. That is the main thing. So we said to UXI for that UXI we are assigning AIs where I lie between 1 to K1. So for N0 we have K1 values are there. This K1 values will be placed on the edge UXI. Okay, UXI where I lie between 1 to K1 respectively. Okay, that is the meaning that for UX1 I have to place the value A1. For the edge UX2 I have to place A2, etc. So likewise I did for VYJ also and WZK also. And then for the rest of the thing, this is the main thing. Okay, for the rest of the thing, that is your wish, you may assign any number. That is, you don't want to bother about that. Just I'm taking for my network, I'm considering f of xi xj is equal to ai, because look at the others. This edges we have to join this one. X1 to X2, X1 to XK, XK1 to XK1 minus 1, and and here also Y1 to Y2, Y3 Y2 to Y3, likewise YK2 to YK2 to minus 1. Okay, and here that Z case also we have to join among themselves. So we can do as your wish, and we can that is labeling also, that is yourself. Okay, we don't want to bother about that one, because step 5, the first line is very much important, because which is related with the N0, N1 and N2. So this I labeled as f of xi xj is equal to ai, and f of xi yj is equal to ai. F of what I did is where the edge started. Edge started xi xj. So it started xi. The edge started with xi. So I assign ai. Look at here yi zj. So I assign bi. Okay, here look at here f of zi zj. So assign ci. So my convenient I'm choosing. This is your choice. You may do anyway. And then decryption algorithm. Now we discussed encryption algorithm. Now decryption algorithm. So what that for the decryption algorithm? So how to find the secret number? First, we have to identify the efficient dominating set. That is a main thing for the network, which will be the efficient dominating set. That is a main thing. So that efficient dominating set is UBW, such that the neighborhood of closed neighborhood of U intersection closed neighborhood of V intersection closed neighborhood of W is equal to MT. And step two, okay, step two, N0. N0 is splitted into K1 subpartitions, which has been assigned on the edge UXI. Okay, so that's why I written here N0 is equal to summation I is equal to 1 to K1 F of UXI. If I add all the values what I assigned on the edge, UX1 plus UX2 values, UX3 values, etc., all the one it will be getting N0 value. That only I marked here. And then N1 also summation J is equal to 1 to K2 F of VYJ. Like N2 is equal to summation K is equal to 1 to K3 F of W is at K. Now last, how to find out the secret number? If you add N0, N1, N3 will be getting N. And suppose that second case, this one, suppose the secret number is not concurrent to 0, then it's not a multiple of 3. Then we have to split into two numbers, X and Y. So X is divisible by 3, Y is not divisible by 3. That Y is separately we have to allot along with that Z member, we have to Z member, Z, the vertex Z. We have that is WK neighbors are there. I have to add another one WK plus 1. For the WK plus 1 Z WK plus 1, I assign the weight Y. So that only I marked here. Here we are seeing that one of the example. So N here I'm considering which is not divisible by 3. So 401 I'm taking. So which is a splitted. This is not divisible by 3. So I have to make it as a split into two numbers. One is divisible by 3. So next one is rest of the values. So X plus Y. Okay, we have to assign. We don't want to give the importance for Y. That's why I'm. It's not the thing that which value, which biggest value that is divisible by 401. That one you have to separate. That is 399. Okay, rest of the value only 2. If I mark the 2, that is a 2. 2 is not a big thing. If you assign very big number, it will affect that. So that's why I did here. Now X into 3 partitions, N0 I'm taking here 159, which is concurrent to 0 mod 3. N1 130, which is concurrent to 1 mod 3. N2 110, which is concurrent to 2 mod 3. Now we are constructing my graph. This is construction is your choice. The number of vertices is same, because number of vertices we have to assign first itself. Number of edges as your wish you may increase it, okay, which does not violate the that is efficient domination member. That is a thing. So here I'm constructing the graph G whose cardinality, that vertex cardinality is 16, and that the size of the graph I'm taking 27 edges present here. And S is here mod under mod 3, so I have to set S is equal to UVW. And then this degree of U is also yourself. You can assign yourself. Just I'm assigning here 5. Degree of V is 4 and degree of W is equal to 4. So here the neighbors of U is 5. That's why I'm taking x1, x2, etc. x5. Here degree of V is 4. That's why I'm taking y1, y2, y4. And degree of W is equal to 4. That's why z1, z2, z3, z4. Which are the neighbors of W. Now I'm defining vertex set. B of G is equal to UVW. These are the members of the efficient dominating set. And for U, the neighbors are 5 neighbors are there. For V, 4 neighbors are there. For W, 4 neighbors are there. So just I'm taking here. So E minimum, as usual, what we discussed, the same thing I written here. There is a x5, y2, y3 z2, and E of G for the minimum, and then I make it as a union. So I have to that is neglect the edges which are affecting the efficient dominating set, which affecting the efficient dominating set. So I neglected. So according to that, I set cardinality of E of G is equal to 27. Now I'm splitting. Okay, neighbors of U are 5. So that's why I am splitting a knot as the 5 members. Okay, 5 subdivisions are there here. 35, 34, 32, 30, 28. Okay, this is also your wish. If we make a partition like that nearly equal number, maybe 32, 31, 30, like that means, so then the your network will be very good network. So that's why I am defining. So the first value A1, the second value is A2, the third value is A3, fourth value is A4, fifth value is A5. Likewise for N1, we have 4 partitions are there, namely as B1, B2, B3, B4. And like for N2 also, so here we have only 3 partition, because for Z, I am considering 4. I'm sorry, here 3. Here 3. So 3 partitions I assign C1, C2, C3. So already we defined. So for the labeling purpose, I defined this function here. F of u xi is equal to ai. Okay, u x1 I have to assign a1 value. What is a1 value? A1 value is 35. U x2 I assign 34. U x3 I assign 32. U x4 I assign 30. U x5 I assign 28. That is A5 value. So likewise for everything. So what I did. And then this Y value is there now. So for Y value, for Z we have 3 members are there. Apart from the 3, I'm taking that for the edge Z W4, I assign the weight as 2, because that 2 is a Y. Okay. Now our graph is there. This is a construction according to that our assumptions. My graph is this one. So look at here, what I marked is in black color vertex. That is the member of the efficient dominating set U. Now you can see the graph, you can understand easily. U, this is U, this is V, this is W. And the neighbors of U are X, X1, X2, X3, X4, X5. Okay, for UX1, look at here, f of UXI equal to AI. So UX1 I assign A1 value. A1 value is 35. I assigned here 35. A2 value is 34. For the second one, UX2 I assigned 34. For A3, 32. I assign UX3 32. Okay, and then A4 30, and then for A5 28. So likewise I assign here that is VYJ also. J lies between 1 to K2. Okay, here 4 edges are there. 4 neighbors of V are there. So VY1, VY2, VY3, VY4. Okay, and then for Z we have only 3 neighbors, but for the Y, there is X plus Y, that Y weight is 2 is there. For that I drawn this edge W is at 4. Along that run I marked the weight as 2. I hope that you can understand. So for N1 also I marked here IN1. So you can see that N1, and then for N3 also. Okay, now we enter into that the decryption algorithm. So how to identify the values? Okay, so this n naught, we know that if we in the network, first you analyze which are going to be the member of the efficient dominating set. Okay, this is U. If you know the definition, you can identify easily U, V, W. Okay, and the corresponding neighbors, and that corresponding neighbors, that is what we labeled in that. Look at that edges. Okay, that edges I'm adding. So n naught is equal to 35 plus 34 plus 32 plus 30 plus 28. You will be getting the n naught value. Okay, and then n1 value, y-axis n naught, n1, n2. So which is 399. But what I taken 401. So x plus y, if I add 399 plus 2, so I'm getting the value 401. So the conclusion I'm concluding here, that is we make it as, when you look at the network, we make it a somewhat difficult one. how to that is break the secret number. First, we have to focus in this way. Once we assign that a naught value, a1 value, that value a naught, a1, a2, etc., and then sorry, a1, a2, etc., a k1 value, and b1, b2, etc., b k2 value, c1, c2, etc., c k3 value. These values are nearly same number. Repetition of the numbers is allowed means that breaking the secret number is somewhat tough. Okay, so it makes some confusion for us. um, so this is my talk. So these are my references. And thank you to all.
An ignited mind is the most powerful weapon on the earth, above the earth, and under the earth. And this is got through education. Education is the most profitable investment for the near future. A very good afternoon to everyone present here. We are conducting 6 days FDP program successfully. At first, I would thanks to Dr. A. Meenakshi Ma'am, Associate Professor, Department of Mathematics, Tech, Rangarajan, Dr. Sakuntala, R&D Research, Institute of Science and Technology. Topic is Applications of Graph Theory in Network. 10-10-2022. Our chief guest, Dr. P. Silvaraj, Professor, Department of Mathematics, Rajalakshmi Institute of Technology, Chennai. Topic, Mathematical Applications is Computing. 11-10-2022, Dr. D. Nagarajan, Professor, Department of Mathematics, Rajalakshmi Institute of Technology, Chennai. Topic, Markov chain with its application. 12-10-2022, our chief guest, Dr. N. Varadarajan, postdoctoral research fellow, Oslo University Hospital, Norway. Topic, Spectral Stability of Nonlinear Wave Solution. 13-10-2022, Dr. A. Silvaraj, Professor, Department of Mathematics, Wales Institute of Science, Technology and Advanced Studies, Chennai. Topic, Introduction to Fluid Dynamics and its Application. 14-10-2022, our chief guest, Dr. V. Sundarapanian, Professor, Department of Mathematics, Tech, Rangarajan, Dr. Saguntala, R&D, Institute of Science and Technology. Topic, Scientific Modeling with Engineering Application. Deem it a great honor and privilege to stand before you to deliver the vote of thanks. On behalf of the entire institute, I would like to thank our management, Tech Multitech, Dr. Rangarajan, Dr. Sakuntala Engineering College, Chennai, respected Principal Dr. V. Rajamani, and Dr. T. Tangeshwari, Professor, HOD of the Science and Humanities. If time is money, then today you have spent millions for us. Thanks to all if you are for making this event successfully. Once again, I thanks to our chief guest and special thanks to Dr. A. Meenakshi Ma'am, Associate Professor, and also our participations. Thank you.
Any questions, please? Anybody having any queries?
Hello, ma'am.
Hello, tell me, sir.
Ma'am, can you go to the slide where you have mentioned the function?
Function. Wait, just a minute. Just a minute. Here, sir. Hello.
I'm not seeing your PPT, ma'am.
Yes, please wait. It's okay, Amma. Is it, sir? What you
Yes,
are
ma'am, it is visible, ma'am.
ask? Yes,
Ma'am,
yes, yes, sir.
ma'am, you have said that function is bijective, ma'am.
Yes, sir.
But suppose if, I'm taking f of x1 comma x2,
Mm.
so that input will assign to the output a1.
Yes.
Similarly, if
No,
I'm
no, no, no,
choosing
no, 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 sir.
x1,
Yes, sir. No, sir. X1, X2, X1, X2. So
yes,
I
ma'am.
is running
That
from
all,
I is not equal to J.
yeah,
I
okay,
is
ma'am.
not equal to J.
Ma'am,
It's a
suppose
different one, na?
okay, ma'am. So I and J are different means we will get A1, ma'am. For any input, we will get A1, ma'am.
No, 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 not like that.
Suppose
I said AI, AI, X1, X1, X2. I is running also 1 to K1.
suppose I'm taking x1, x2.
Yes, yes, X1,
So
X2.
the output will be A1, ma'am.
Yes, A1.
And at the same time, I'm taking x1, z1. Down you have in the second line you have
Wait,
mentioned
wait.
f of x.
X1, X1.
X1 is that one something, ma'am.
Yes,
Here
sir.
also, the output will be A1.
XI. Okay.
So it may be, I'm not sure.
No,
I
sir.
think
No,
it's
sir.
while the
Actually, we have to assign the values. Okay, which will be nearly same if repetition allowed here. But we cannot here we are taking A1, A2, A3, etc. AN are there. Okay, AIs, all AIs are different, all BJs are different, or all CKs are different. You got it?
yeah, okay, ma'am.
Then, sir, any doubt?
Okay, ma'am.
Any
That's
other
it, ma'am.
question?
Thank you, ma'am. Thank you for
Any other questions?